Welcome to lecture number 44 of the course on nonlinear structural analysis, theory and applications. Let us recall what we have done in the previous lecture. So, in the previous two lectures, we have started discussing distributed plasticity approach. Okay. We have looked at the stiffness based or displacement based formulation, and we have looked at the flexibility based or force based formulation in the previous lecture. Okay. And in this lecture, what we will do, we will revisit the Fibre-Section analysis that we did long back, okay, and then talk about numerical integration, because as you see, we have to do some integration to get the element tangent stiffness matrix, okay, for the displacement based element, and also the element end forces to you have to integrate the section responses along the length of the element. Okay. So, this is the content for this lecture. So, let us get started. So, as I was saying, in the displacement based element, we have to evaluate this integration. Okay. S bar x is the section force vector, and A transpose x, A x is the matrix of Ceph function, okay, and this is the element end force vector, and this is the element tangent stiffness matrix for displacement based element. Okay. On the other hand, for force based element, we have to evaluate this integration, where B x is the force interpolation function, matrix of force interpolation function, and F bar x is the section tangent flexibility matrix. And this also we have to determine, which is basically the element residual deformation vector, and this is the section residual deformation vector. Okay. How do we do this integration numerically? Note that we can do a section analysis to get S bar x and K bar x, okay, using Fibre-Section analysis, which is the preferred approach. We have done this in lecture 24 to 29. I shall revisit in just a little bit. Okay. You can also use stress resultant plasticity theory, which I briefly covered in lecture 38 and 39, and also talked about the limitations there. So, therefore, Fibre-Section analysis is a better approach. In principle, this can be used, but no one uses this typically. Okay. So, let us revisit the Fibre-Section modeling pictorially. So, let us say I have a nonlinear beam column element, whether it is flexibility based or stiffness based does not matter. Okay. So, this is theta I, the rotation at end I, this is theta j, and this is delta in this simply supported basic or deformation coordinates, right. And I will be discretizing this into number of sections. How many sections? We shall see. Okay. So, if I consider any one cross section, so this is what I am showing here. This cross section is discretized as shown. So, this is one fiber, then this is the another fiber, and so on. Okay. And this is the reference axis, which is typically taken as the centroidal axis, and this cross section is subjected to axial force n x, because this is, let us say, the distance x, okay, and the bending moment m x, right. And this is the distribution of the strain. Okay. Let us say at the centroidal axis the strain is epsilon. Okay. At any distance y, this is the fiber centroid, CG of the ith fiber. Okay. So, at the CG of the ith fiber, which is denoted by yi from the reference axis, the strain is epsilon I, which I can compute as epsilon, my tensile strengths are positive. So, epsilon minus psi is the curvature times this distance yi. Okay. So, this is epsilon I. Once I know the strain for each fiber, which are all uniaxial fiber, okay, now I can model the fiber response using the different uniaxial material models that we have studied earlier in the course. Okay. For example, for a steel fiber, I am showing you a bilinear hysteretic stress strain response. Okay. So, this is sigma and epsilon. If you know this, let us say if it is here, then you know what is sigma. If it is here, you know what is sigma. You do a state determination for every fiber in the cross section. Okay. Then what we do, I will show you. Okay. We have done examples in OpenSys earlier also, but now I will show you theoretically what is done. Okay. For a reinforced concrete, let us say I am showing you reinforced concrete T beam, again in the simply supported basic or deformation coordinates, where let us say this is a cross section and this cross section is modeled something like this. Okay. Here you have multiple fibers. So, this fibers I am showing 2 fibers here which are unconfined concrete, and here you have concrete fibers which are let us say confined concrete, then you have steel fibers. Okay. So, the stress strain response of steel fiber is let us say something like this. Again you can use Menegotto-Pinto, you can use Ramberg-Osgood depending on the your objective of the analysis. And for confined concrete fiber, let us say this is the stress strain response. So, every fiber has a stress strain response associated to it. Okay. And this is for the unconfined. Let us say the reference axis is again passing through the centroid of the cross section, and this is the strain at the centroidal axis, and this is the strain at the CG of ith fiber, which is epsilon minus psi into yi, where yi is the distance from the reference axis. Okay. Following are considered positive as before. Sagging moment is positive, curvature convex down is positive, that means a smiley face. Tensile fiber strains and stresses are positive, yi measured upward from reference axis. Okay. So, these are my sign convention, and like I said, reference axis is generally taken as the centroidal axis. Okay. So, what is the objective? The objective is to determine the fiber section state and the tangent stiffness matrix. Okay. So, given V bar x, that means the given section deformation vector which is strain at the reference axis and the curvature, okay, and the incremental section deformation vector delta V bar x determine the section tangent stiffness matrix and section incremental force vector delta S bar x. Okay. Assumptions are plane sections remain plane, and therefore, we got that linear double triangular strain distribution. Each fiber has a uniaxial sigma epsilon relationship, okay, as I have shown you earlier. So, the strain at the ith fiber, which I have already shown you, epsilon I is epsilon minus psi into yi, where epsilon is the strain at the reference axis, which if I write the deformation vector Vx is basically epsilon and psi, okay, and this is the curvature, right. Now, the incremental section axial force, how do I get it? Well, if I integrate the stress acting over a small area dA, integrate over the cross section. So, this is for analytical solution, because I have discretized into number of fibers. So, I can replace this by a summation for I is equal to 1 to nf number of fibers. So, ai is the area of fiber I, and delta sigma I is the incremental stress for the ith fiber. Okay. Now, this is the one we will use for doing the state determination for the section, and then I can rewrite this as the tangent modulus for the fiber stress strain response multiplied by the incremental strain for the ith fiber. Okay. Then this can be further written as delta epsilon minus delta psi into yi, where delta psi is the incremental curvature, this is the incremental strain at the reference axis. So, this I will be using for state determination, this I will be using for tangent stiffness matrix formulation of the fiber section. Okay. Now, for the moment, so this negative sign appears because of the sign convention that I have taken. So, integration y d sigma dA. So, this is the force multiplied by y is the moment and integrated over the cross sectional area. This I will now replace by this summation because of the fiber section discretization. So, basically ai, yi and del sigma I. Okay. So, this I will use for state determination, and then delta sigma I can rewrite just like before, tangent modulus multiplied by delta epsilon I, and delta epsilon I is replaced by that minus delta epsilon plus delta psi yi, and this minus basically this is absorbed inside. Okay. So, now incremental section forces from equation 2a and 3a, that means this equation and this equation. So, on the left hand side I have delta nx, delta mx I can rewrite, which is my delta s bar x, delta nx, delta mx is summation fiber I is equal to 1 to nf 1 minus yi multiplied by ai delta sigma I. So, that means for each fiber you determine what is my incremental stress multiplied by the fiber area, and then you do this, that will give you incremental axial force and incremental moment. So, this gives us the section forces at the section at a distance x. Okay. So, the updated section force is the previous plus this incremental one. Okay. Now, if I combine the other two equations, that means this equation and this equation, then what do I get? Well, I can write again delta nx delta mx, the incremental section forces is equal to this times delta epsilon delta psi. Basically what I am doing, I am writing this is equal to delta epsilon and delta psi are taken to the right hand side in a vector, and then summation ai ei, this is one quantity, then summation ai ei yi with a minus sign is the next quantity. That is what you see here. Okay. Similarly, for the next row, right. Now, if you see what is this incremental section force vector is equal to a matrix times incremental section deformation vector. That means, what is this matrix? This is nothing but the section tangent stiffness matrix. So, this is how OpenSys or any other finite element program determines the tangent stiffness matrix and the state of the cross section. Okay. And you can compute all of this numerically, okay, where NF is the number of fibers. Okay. So, in the force based or flexibility based approach, we need the section flexibility matrix. The section tangent stiffness matrix can be inverted to get the section flexibility matrix. Okay. For linear elastic cross section, as you remember, k bar x for elastic is AE 0 0 EI. Do I get this from the previous slide? Let us take a look. So, this one, if I apply for linear elastic cross section, okay, so what happens? This summation will give me AE, because E is not changing, you are summing over the cross section. So, this will give you A into E. This one will become 0, because yi is measured from the reference axis going up and then going down, right, and reference axis is passing through the centroid. So, for elastic this is going to be 0, this is going to be 0, and this is going to be simply EI. Okay. So, that is what I am showing. So, this is AE, this is 0, and this is going to be EI. Okay. So, that is how you get that, right. Now, let me talk about the numerical integration. Okay. So, again I am showing you this slide that we have to do this integration, we have to do that integration. What I have talked about so far, how to determine this, how to determine that, and how to determine this quantities. Okay. So, what is the idea? If you have a function f x, right, all of us know the trapezoidal rule. Let us say this is the function I am plotting f x, right. I want to integrate this function between a to b. If I use the trapezoidal rule, then what I do? I evaluate the function at a, I evaluate the function at b, and then compute this area, right, which is the integration. But as you can see, there is a large error here, right. So, this is the standard trapezoidal rule. Okay. We can improve this integration by actually defining this point anywhere in between. For example, the same function I am integrating between a to b. Now, what I will do? I will evaluate the function somewhere here and here, so that this is the additional area that I have incorporated, and this is the area, unshaded area, which I have not taken. So, that means if I say that this is the positive area that I have added, this is the negative area, the objective is to balance them out, so that I get the area under the curve quite accurately. So, that is the objective of this improved integral estimate, which is the Gauss quadrature, which I will show you. So, trapezoidal rule is not used for doing the element integration or integration of section response. We use Gauss quadrature, which uses this idea where the integration points could be anywhere within the element. Okay. So, let me show you further. A function f x can be numerically integrated using Gauss quadrature like this. So, 0 to L, remember our integrations are from 0 to L, where L is the length of the element, 0 to L f x dx. Okay. First, what I will do, I will change the integration limit. Instead of 0 to L, we would like to do it between -1 to +1. So, how do we do that mapping? Well, x is defined as L by 2 plus 1 plus psi. Okay. Now, if you set x is equal to 0, then psi is equal to -1. If you set x is equal to L, then psi is equal to +1. Okay. And that is the limit. So, this becomes -1 and this becomes +1. If you do dx, then you get L by 2 d psi. So, therefore, L by 2 comes out, you get f psi d psi. So, this is converted to that. Now, this integration can be calculated like this: summation I is equal to 1 to n wi, a weightage, times the function f evaluated at some discrete point psi I, okay, where how many points? We are taking n number of points. Okay. So, psi I, wi and n are locations, weights and number of integration points. Integration point means number of cross sections that I am considering along the length of the beam. Okay. So, there are two types of integrations that are commonly used. One is called Gauss-Legendre integration and the other one is called Gauss-Lobatto integration. So, Gauss-Legendre integration is exact for polynomials of degree up to 2n minus 1. That means, I am talking about this polynomial f x. So, this Gauss-Legendre is exact for polynomials of degree up to 2n minus 1, where n is the number of integration points. Okay. So, that means, let us say if you are integrating a second order polynomial, then how many integration points are needed? Well, if you take one integration point n is equal to 1, then this becomes unity, right. So, a second order polynomial cannot be integrated exactly using single Gauss-Legendre integration point. If you take two integration points n is equal to 2, then this becomes 2 times 2 4 minus 1 is 3, right. So, a second order polynomial can be exactly integrated using two Gauss-Legendre integration points. Okay. So, for single point Gauss-Legendre, epsilon I is at the center, it is only 1 point and the weight is equal to 2. For 2 points, this is plus minus 1 by square root of 3, which is actually 0.577 and so on, and the weight is 1. If you take 3 integration points, you see they are all placed symmetrically. One is at the center and the other 2 are at this distance, and these are the corresponding weights. So, for 4, 5, these are the weights given. Okay. Observe that if you sum the weights, let us say if you sum these weights, you have to take this 2 times, you will always get 2. Okay. And the integration points are symmetric about the origin. For more number of integration points, you can go to table 25.4 of this handbook. Okay. That reference is given at the end of this lecture slides. Okay. So, for a 5-point Gauss-Legendre integration scheme, I am showing you on a beam column element in simply supported basic or deformation coordinates. So, this is the integration point at 0, then this integration point is minus 0.538 and this one is at plus 0.538, this is the corresponding weight. Okay. Similarly, these two are the other integration points, as you can see they are placed symmetrically. So, what you have to do? You have to calculate the value of the function at psi 1 is equal to this much, then multiply by w 1, similarly add it w 2 multiplied by function evaluated at this and so on. Okay. I will show you an example in just a little bit. So, note that there is no integration points at the ends of the element. Okay. So, this is commonly used in displacement based elements. The question is, how many Gauss-Legendre integration points are required to get exact solution for a linear elastic displacement based or force based beam column element. So, if there is no material nonlinearity, you are taking a displacement based element or a force based element, how many integration points are necessary to get the exact solution. So, let me show you that. Let us say for displacement based elements, so if I try to derive the stiffness matrix using exact integration. So, this is my A x that we have already gone through, and this is my k bar. Here I cannot write like that. So, therefore, I am writing k bar because this is done in MathCAD. So, EA 0 0 EI. Now, if I do the exact integration 0 to L A transpose k bar A, then this is what I get, which I already stated in previous slides. Okay. Now, if I use the Gauss-Legendre integration, so what is the polynomial here? You see, I am doing A transpose x and then here also AX. So, this is linear multiplying again linear. So, then the order becomes 2. So, it is a quadratic polynomial. So, we need at least 2 integration points. So, if I take n is equal to 2, then this Gauss-Legendre is going to be exact up to 3 degree of polynomial. Now, we have a quadratic polynomial. So, naturally, I should be getting the same answer. So, for a 2-point Gauss-Legendre, these are my psi I value, as I was saying, 1 by square root of 3 minus 1 by square root of 3, and weights are 1 1. So, now I convert it to x, L by 2 1 plus psi, which is this, and then I do this integration. So, as I was saying, L by 2 summation W I A transpose k bar A. Now, here we have 2 points. So, this is one and this is the other one. If you evaluate this, it gives you exactly the same stiffness matrix that I have got here. So, you can see that 2-point Gauss-Legendre gives you the exact solution for the displacement based beam column element, which is elastic. Okay. Now, let me talk about the flexibility matrix using the exact integration. So, this is my force interpolation function and this is f bar. If you compute this integration, this is what you get, which I already discussed in the slides. Okay. Now, if you use 2-point Gauss-Legendre integration, then in this case you have 2n minus 1. So, 2 into 2 minus 1 is 3. So, again, what is the order of the polynomial? This is first order, you are multiplying it twice. So, you will get second order polynomial. Okay. So, this is 1 by square root of 3, same as before. You compute x and then you do this computation. What you see, you basically get exactly the same tangent flexibility matrix, which is for elastic. Okay. And this is identical to that. Okay. So, that means using a 2-point Gauss-Legendre, you can get the exact solution for displacement based or force based nonlinear beam column element. Okay. Now, let me talk about briefly the Gauss-Lobatto integration, which is exact for polynomials of degree up to 2n minus 3. As you can see, this is less accurate compared to the Gauss-Legendre. Okay. So, here you can have 2 integration points. The locations are at the 2 ends, plus 1 and minus 1, and the weights are 1. For 3 integration, 1 is at the middle and 2 are at the ends. So, in this case, you always have 2 integration points at the ends of the element. Okay. Again, observe that if you sum the weight for every case, the summation is equal to 2. Okay. And you can see this table in the handbook for more number of integration points if you are interested in implementing yourself. Okay. So, in this case, I am showing you a 5-point Gauss-Lobatto integration. So, one is at the center and then here at minus 0.655 and this is plus 0.655. These are the weights and you have 2 integration points at the ends of the element. Okay. So, this is less accurate compared to Gauss-Legendre for the same number of integration points as I showed you, but it is superior when elements ends are needed to be included in the integration. Why? Because remember, in a seismic resistant moment resisting frame, okay, the ends are where the bending moments are maximum, you will get plastic hinges there, right. So, therefore, you need to include the ends. Okay. This Gauss-Lobatto is used in both displacement based and force based element. Now, if I ask how many Gauss-Lobatto integration points are required to get exact solution for linear elastic displacement based and force based elements. So, let me show you that. So, this is for the Gauss-Lobatto. Okay. So, I need at least 3. Why 3? Because the order of accuracy is 2n minus 3. So, if I take 2, so 2 2s are 4 minus 3 is only 1. So, 2 integration point will give me exact solution for first order polynomial, but I have second order polynomial. Therefore, I need to use at least 3 integration points. So, then I can get exact solution up to third order, but we have second order, which is fine. So, these are my integration points, two ends and one at the center. These are the weights. Okay. So, calculate x and then you do the summation. What you get? You get exactly the same element stiffness matrix in the basic or deformation coordinates. For this is for the displacement based element, which I already showed you earlier for the Legendre. Okay. Now, let me go to the force based element. Okay. So, for the force based element, we have to get the flexibility matrix. So, if the stiffness matrix is obtained correctly, then flexibility will also be obtained correctly. So, this is psi w and x, and you compute this. I will share this PDF file with you, so that you can spend more time on this and you are getting exactly the same answer. Okay. So, that brings us to the conclusion of this lecture. So, in this lecture we have revisited the fiber section analysis and we have talked about numerical integration. We have talked about two schemes, one is Gauss-Legendre, the other one is Gauss-Lobatto. In Gauss-Legendre you do not have integration points at the ends of the elements, whereas in Gauss-Lobatto you always have two integration points at the ends of the element. Gauss-Lobatto is less accurate compared to Gauss-Legendre for the same number of integration points. Okay. And remember, the integration points are nothing but your cross sections that you are considering along the lengths of the element. Okay. In the next lecture, what we will do, we will compare the performance of displacement based element with the force based flexibility based element, and we will do examples in open Cs, and then we will talk about the limitations of both the method once again and see what else can be done. Okay. So, this is one reference, the handbook, where you can find out for more number of integration points what are the locations and the weights. With that, thank you and see you in the next lecture.